to Algebra II with Mr. Clausen. Today I want to talk about graphing parabolas by analyzing quadratic equations. And to get started, I want to go through a few examples of graphing parabolas and what we want to look for in quadratic equations in order to graph them. And then I'll finish off the video by talking about how to create some equations using some limited information examples. So without further ado, I want to get started here because I have a lot to talk about. Now, whenever we're looking at a parabolic function or quadratic equation, such as the one I have here, I want to think about this equation as it normally is in standard function notation. So standard function notation we talked about previously can be listed as f of x is equal to ax squared plus bx plus c. And whenever I'm looking at a standard function like this, I want to compare it to the equation that I have and identify what the a, b, and c value is in the given context that it's being presented in. So if I look at the x squared term here, I know that the minus sign would represent the a term, and so the a term in this given case is equal to -1. Now, with that said, I see that a is equal to -1 and that there is no single x term here. So that tells me that b is equal to 0, and c here is our constant, and that is equal to -1. And with each piece of information that I have present here, I can learn something specific about this given quadratic equation and what the parabola will look like. So specifically, a tells us a couple different things. It tells us whether the parabola opens upward or if it opens downward. And if a is greater than 0, it opens upward. And if a is less than 0, it opens downward. And if a is equal to 0, then you wouldn't have a parabola at all. You just have a straight line, which would represent a linear function. Now, if we're looking at this and we see that we have -1 for the a term, I know that I'm going to fit into this given parameter. And the -1 also tells you the relative steepness of the curve. All right, so 1 is pretty standard. And so you would decrease at a typical rate of a quadratic function. So, and I'll get into that a little bit later, but this is pretty standard situation that we have here. Now the b value is not of any particular importance right now because it's 0, but the b value is particularly useful for determining the axis of symmetry. All right, and so if you want to make a note of that, you may. I'm going to get into a couple examples later and how that looks, but right now I'm just going to focus on the a and the c terms. Now the c term specifically is going to represent your y-intercept. C is going to represent your y-intercept. And so if we're looking at this, we can figure out some things pretty quickly. Now, if b is equal to 0, the reason I say we're not really worried about the axis of symmetry is because the axis of symmetry is at 0. So if the axis of symmetry is at 0 and your y-intercept is -1, while your vertex is at -1 for your term here. Okay, and so I can tell right away that this is my vertex based on this piece of information. Given that b is equal to 0, which tells me the axis of symmetry is at x equals 0, and that c is equal to -1. And now with this, another thing that I can do is I can go and graph some points using a t-table. Now if I go and graph x and y, a real quick thing to do is I can just go plug x is equal to 0. If I plug x to 0, this will cancel out. All I have is -1. And now, since I know that this is also my vertex, I just have to test a couple other points to figure out some corresponding positions. So if I plug, let's say, 1 in for x, all right, 1 squared, keep in mind that the parentheses are technical here, so -1 minus 1 is -2. If I plug 2 in here, all right, that would be -4 minus 1, which would be -5. And what I want to point out here is now if I go 1x -2 and 2x -5, I can now graph half of the parabola here. And the other thing I want to point out is that we understand that corresponding points will be directly across. So we don't even need to use the t-table. We can just pick the other points. And now I just really quickly graph this parabola by analyzing the equation. So a second example that I want to point out here. Again, I see the a term is less than 0. So that tells me that it is downward sloping, and it's pretty steep because now the term is larger in magnitude, and we'll talk about how we can figure that out pretty quickly. B is equal to 0, so the axis of symmetry is equal to 0. And our C term is equal to 12. Okay, so since the axis of symmetry is at 0 and the y-intercept is at 12, we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We'll estimate where that point is. And then if we want to just plot a couple points here, again with the t-table, all you really need to do is find just a couple points. All right, so x at 0, y is equal to 12. If we plug 1 in for x, we'll go 1 squared. That'll be negative 5 plus 12, which would be 7. If we go 2, that would be 4 times negative 5, which would be negative 20 plus 12, which is going to equal negative 8. So really, with a couple very quick pieces of information, we know that's 1 point, and at 2, we're going to be at 4 and 8. And so we can very quickly see that this half of the parabola looked like that, and then its mirror image would just have these corresponding points that we can go and trace out very quickly. All right, and with very little information, with very little analysis, I can actually graph this quadratic really easily by just seeing that a is negative, so it tells me that the parabola is opening downward, and by the fact that there is no b term, the axis of symmetry is at x is equal to 0. Now, with this, I don't want you to get into the assumption that every situation is going to have no b term. So I'm going to introduce another example here where we can again look at our function notation, and we're going to look at a situation ax squared plus bx plus c. And here we have a is equal to 1, b is equal to 2, and c is equal to 1. And it's just based off of the terms that we have present on this given quadratic equation. Now, since we know now that a is greater than 0, we understand that the parabola should be upward opening. And if we know that's upward opening, that gives us a piece of information. But since we have a b term now, we have to take into consideration what the axis of symmetry is. So if we have the axis of symmetry, the axis of symmetry is always equal to x is equal to negative b over 2a for any given function that is in standard notation. So if we have 2 for b and 1 for a, we can write the axis of symmetry for this as negative 2 all over 2 times 1. And so the axis of symmetry for this given example is at x equals negative 1. All right, and that's a formula that you're going to want to write down on your note card for an upcoming quiz or an exam, is that your axis of symmetry is always at x equals negative b over 2a, which in this case equals negative 1. And that's why when the b term is equal to 0, well, you have 0 in the numerator, and then you would just have no reflection that would occur. And so we know the axis of symmetry, and now we also know the y-intercept of 1. So we can still say that the y-intercept is the point where the b and the a term would be canceled out when x is equal to 0, is located here. So the big thing I have to really find right now is where is the vertex of this given function. Now that we have a b term, this is really the big thing that we need to find. So the thing you need to take into consideration here is that the x value of the vertex is always on the axis of symmetry. So if you want to find what the y value is on the axis of symmetry, you just plug it in to the given equation. So we could just say f of x and plug -1 in for x, and then we could say -1 squared plus 2 times -1 plus 1, say 1 minus 2 plus 1 is equal to 0. And this would represent the y value of your vertex. And so the vertex for this given situation is simply going to be -1, 0. And with this, -1, 0, we understand this basic shape, and we know a corresponding point is going to be on the other side. And so really all I need is one more point, and I can very easily graph this function. So let's just say, for example, what is the function when f is equal to 1? That would just give me one other point. So 1 squared plus 2 times 1 plus 1 is going to equal 4. Very standard formation. Corresponding point directly on the other side. And I would consider this very acceptable for tracing out a parabolic function and seeing what it looks like. We have a situation now where we've had a little bit of shift because of the b term that's present in the quadratic equation. All right, let's look at a little bit more interesting example here where there is a fraction involved. All right, so we have, again, the main things that we want to be looking at is the a term greater than 0 or less than 0. If it's greater than 0, it opens upward. If it's less than 0, it opens downward. All right, it opens downward. So we're going to check that box there. And now the second thing that we have to find is the axis of symmetry. The axis of symmetry is always equal to x equals -b all over 2a. In this given case, b is equal to 6, and a is equal to -3 over 4. So we do a little math. We see that we have -6 all over -6 over 4. The 6's would cancel. The denominator becomes a numerator. And we have the axis of symmetry at x is equal to 4. Once we have the axis of symmetry, the next step is to find the vertex. Well, since the x value of the vertex is at the axis of symmetry, all we need to do is plug that into the function. So we're going to plug -b over 2a into the function that we have up here, assuming that y is equal to f of x. So really what we're going to do is we're going to plug in 4 in for -3 over 4 times 4 squared plus 6 times 4 plus 6. And what we'll get is -12 plus 24 plus 6. That'll be 30 minus 12, which would equal 18. So the vertex is 4, 18. And so now we can trace some of these things, the axis of symmetry. All right, and what I'm going to do is I'm going to say this is 10, and this is 20. So we have 1, 2, 3, 4. So at 4, 18, we have a point. At 6 over here, we have one y-intercept, a point corresponding would be over here at 8. And I feel like I should find one other point here. So what I'm going to do is I'm going to choose 2 as that other point, and just picking a space in between. All right, and there I can go -3 over 4, 2 squared plus 6 times 2 plus 6. That'll give me 4 over 4, so I have -3 plus 12 plus 6, and that's going to give me 15. So that's going to give me a point right here, and corresponding to it right there, because it's, again, it's that equidistant point from each side of that mirror image. And now we can very easily graph this out. And again, get a very clear picture representation of what this function would look like from a very quick piece of analysis. I feel like if you have 3 points that you can have as your representation, one of them being your vertex, just find the other corresponding points and draw out the quadratic equation or the parabola. Now I want to take a couple minutes here to talk about how to create an equation using limited information. So let's say, you have an example and you want to find the missing term here of C, given that you have the vertex of your equation and some basic information about the quadratic equation that you have at hand here. And so if you ever have a situation like this where you have to find some of this information, I kind of implied it with some of the other examples where it was like, well, if you need to figure out some points, just plug some things in. For example, plug in the axis of symmetry into your equation and it'll give you the y term of your vertex, since the axis of symmetry is the x value of your vertex. So if we look at a given situation like this, all we really need to do is, if you want to find a missing variable like C, well, you just take the vertex and you plug it right into your equation. So you plug -4 in for y and 3 in for x. And so if we do that here and go -4 is equal to 3 squared, -6 times 3 plus c, you have now plugged in a number for every variable present except for your unknown variable. And all you simply have to do in these given circumstances is just plug and chug and solve for c. So in this case, we'll go -4 equals 9 minus 18 plus c. You can go combine like terms. We can solve, add 9 to both sides, and find very quickly that c is equal to 5 in this given case. And you can find variables like this very easily. A second example that I want to go over very briefly is, let's say you have a quadratic equation where you have y is equal to ax squared plus c with a graph that has the given points. Now they don't tell you anything about these points necessarily, but the thing I want to point out here is that it doesn't really matter what the points are. What I'm going to point out is that you have 2 unknown variables. And with that, what you need to know is that for each unknown variable you have present, you need 2 pieces of info to go with that. No more, no less, just 2. We know the basic structure of the quadratic equation, and we know 2 of the data points. And so all you need to do at this point is you just need to plug some stuff in. All right, and one thing I'll tell you is there's no b term, so the axis of symmetry is that x equals 0. So what that tells you is this is your vertex. Now you don't even need to know that. All I would say is just plug in that term. I think that's the easy term. If there's a 0 present, just use that one first. I think that's just going to make your life a little bit easier. So if we plug the vertex into the equation up here and we combine these 2 pieces of information, we'll find that when y is equal to 2 and you have 0 in for x, that's going to cancel out your x squared plus c. What that'll do is anything multiplied by 0 is 0, and that tells you right away that c is equal to 2. You just got one of your 2 variables figured out here. So now what we're going to do is we're going to leave c in place here, and we're going to go now and plug that piece of information along with this one, since we figured out a variable, and therefore 5 equals a times 3 squared plus 2. And what you should see here now is that the a variable here is our second piece of information, but is also the only variable that remains. So now we're going to just say 5 is equal to 9a plus 2. We can go and do some rearranging. Let's just move this up here and say 9a is equal to 3. Divide both sides by 9 and quickly find that a is equal to 1/3. And you just found the other term. So the actual quadratic for this would be y is equal to x squared all over 3 plus 2. And that would represent the quadratic equation for this given circumstance. So with that said, I hope that you got a fair amount of information from this video. To just quickly recap, I want to point out some of the basic things that you should know about graphing quadratics. So again, if a is greater than 0, you should know that the parabola will open upwards. If a is less than 0, it will open downwards. Your axis of symmetry is always going to be represented by x is equal to negative b over 2a when we're looking at equations in standard function notation, which is represented by f of x is equal to ax squared plus bx plus c. And if you want to find the vertex for a given point, we'll just plug the axis of symmetry into the equation to find the y value of your vertex, and the axis of symmetry is the x value of your vertex. I hope that this video gave you a great introduction into quadratic equations and how to graph parabolas, and with that said, let's do some math.